We're going to think small here for a minute. Very small. Subatomic. Imagine an infinitesimally tiny particle, a neutron, slamming into a much larger atom. As that atom splits apart, it releases huge amounts of energy. Enough to power... nothing? At least nothing that you and I can see with the naked eye. One atom is very, very small. And while it does release a huge amount of energy relative to its size, we'd need to split a lot more open before we get any visible results. So I'm probably going to sound pretty dumb when I say that I'd never really stopped to think about how the phrase splitting the atom wasn't just about one atom. It's about splitting a lot of them in really fast succession, known as a chain reaction. Which, of course, now that I think about it, makes total sense. But if atoms are so ridiculously small, what made us realize they'd be useful for both generating power or building bombs? And for that matter, what is an atom? I'm Laura Krantz, and this is Wild Thing, Going Nuclear, a series about the power of the universe, contained in the tiny little package of the atom.
You and I are living in the atomic age.
The endless debate over harnessing that power,
the mysteries of the universe,
and whether we humans are responsible enough to mess with it.
Of benefit or of destruction, of good or of evil.
To understand what happened to the doomed SL-1 reactor out there in the hinterlands of Idaho, we first have to understand what happens inside an atom and how exactly we split it open to get energy. So, we have to start this season with a little science. But don't worry if that isn't your favorite subject. This lesson in physics is going to be about as simple as it gets. Now, for starters, just what is an atom? At the most basic level, an atom is generally considered the smallest unit of matter. Anything that takes up space or has volume is made of atoms. The idea that matter is made up of tiny particles appeared independently in both ancient India and in ancient Greece, roughly 2,500 years ago. The word atom is Greek. It means indivisible, which is what we thought atoms were until pretty recently. Ancient civilizations, of course, couldn't actually prove atoms existed. They didn't have the technology. But scientific experiments done in the mid-1600s proved those early ideas right. It took us a couple more centuries to figure out that atoms are themselves made up of even smaller particles, subatomic particles.
Electrons and protons and neutrons. But then, of course, the atoms, they're not the fundamental building blocks anymore.
That's Dr. Pete Markowitz. He's an experimental nuclear and particle physicist and a professor of physics at Florida International University.
So the thing about atoms is that an atom is going to be only one element in there. So maybe it'll be hydrogen or maybe it'll be iron, but it won't be steel because steel has nickel and iron in it. So it's a compound. And so in some sense, atoms still are fundamental in that way.
Pete has had decades of experience working with atoms and their parts, and it's those parts that end up being the key to some world-changing science.
So an atom is built up out of smaller pieces, and the smaller pieces are protons and neutrons in the center, and the center we call the nucleus, just like maybe the center of a biological cell is called the nucleus of the biological cell. And then it's got a sort of swarming cloud of electrons which circle around that center.
That classic image of the atom, of electrons orbiting the nucleus like planets around a tiny sun, well, that, it turns out, is a big fat lie.
That's not really the way we think it works now. Now we think that the electrons are more like a cloud that surround the center of the atom.
Okay, so like a buzzing cloud of gnats kind of thing.
Yeah, and it really is sort of a buzzing cloud in the sense that they're always moving.
As he said, the center of that buzzing cloud is the nucleus, which is made up of protons and neutrons. This is going to get a little technical in here, and as someone who worked very hard to avoid taking high school chemistry and barely made it through physics, I know it can feel a little daunting. But this information will help later on down the road. Deep breath. Here we go. So the number of protons that an atom has tells us where it fits on the periodic table of the elements. That number is kind of like a fingerprint. It's unique to each element. So for example, hydrogen has 1. Helium has 2. These are considered lighter elements, and uranium, which we are going to hear about a lot, has 92 protons, making it relatively heavy. Now, While the number of protons is always the same for a specific element, the number of neutrons can change. Basically, these are different varieties of the same element, and they're called isotopes. So for example, in the case of uranium, the most commonly found isotope is uranium-238, which has 92 protons and 146 neutrons. Uranium-235 is another isotope. It has 92 protons, but only 143 neutrons. You can think of isotopes as belonging to the same family, similar but not identical. And the total number of protons and neutrons that an atom has determines its mass, which we refer to as atomic mass. When you count up the number of naturally occurring elements and each of their isotopes, there are roughly 339 distinct kinds of atoms that we've identified so far. The majority of those are considered stable, which means that they generally have a similar number of protons and neutrons in the nucleus. Why does that matter? It helps to think about magnets for a second. If you've played around with them, you know that if you try to put two positive or two negative ends together, they'll fight you every step of the way. Protons carry a positive electric charge, and like our magnets, all those protons packed into the nucleus should be pushing away from each other. But in a stable atom, they don't, because the neutrons, which are neutral and have no electric charge, act like a sort of glue and hold the nucleus together. So what happens if you don't have enough neutrons in an atom, or too many? Well, that atom becomes unstable. To borrow from the poet William Butler Yeats, things fall apart. The center cannot hold. Of the 339 distinct types of atoms mentioned above, 87 of them are considered unstable, and they are sometimes called radionuclides because they are radioactive. The force that bonds a nucleus together is very strong, but in the heavier elements like uranium, the number of neutrons and protons is much larger, so the nucleus is much bigger, and it has a harder time holding together. This pushes the atom out of balance and makes it unstable. And as the nucleus strains to keep it all together, the atom becomes more energetic, meaning its subatomic parts start shifting around into new positions. But atoms don't want to be energetic. It's almost like they're fundamentally lazy and don't want to work that hard. So they try to calm down and regain a level of stability by throwing off protons, neutrons, electrons, and even light waves. Think of a slingshot. You've pulled the strap way back and you're holding a marble in place. There's a lot of tension, a lot of potential energy contained in that stretched out strap. But ultimately, the strap is straining to return to a state of low energy. So when you let go of the strap, it snaps back into that lax state, and your marble goes zipping off into the ether. That marble, in this example, is called radiation.
Radiation is the particle given off when we go to a lower energy state. So the radiation itself can be anything from a particle of light to a proton or neutron, or even an electron. And so radioactive nuclei are those which would like to go to lower potential energy states, and in doing so will give off a particle of radiation.
Okay, so they're shedding protons, neutrons, or electrons.
Yeah, and sometimes when they shed it, they're going to split in half too.
You might have heard of alpha and beta particles and gamma rays. These are all examples of radiation, and we're going to get into those in more detail in a future episode. But if you take nothing else from this monologue on atoms, remember that unstable atoms give off energy, and that when they shed that excess energy, they can sometimes split in half, a process known as fission.
They will fission, they'll split. They almost never split exactly in half. But maybe one would split to something where like they've got 90 protons and neutrons, and the other one might split to something which has like 140 protons and neutrons. And you might get another 3 or 4 or 5 neutrons coming out of it on top of that too.
These extra neutrons are just loose marbles zinging off in different directions and smacking into other atoms.
And so those neutrons then are probably going to get stuck into another nucleus from a nearby atom and cause another splitting. And if we got at like just one neutron, then we could only cause one splitting at most. But if we got at like 3 neutrons, then we could split 3 different atoms. And if each of those 3 also gave off 3 neutrons on average, so we could have like something where it would like go faster and faster, and we'd be splitting more and more atoms. That's what we mean by a chain reaction.
And the idea of a chain reaction had the physicists who first discovered it all kinds of excited, because every time one of these atoms splits, it releases energy. How much? Well, as we pointed out early on, for one atom, it's not really that noticeable. But given an atom's size, it's definitely not insignificant. And here is where the most famous equation of all time comes into play: Albert Einstein's E equals mc squared. A confession. For as well known as that equation is, I'm a little embarrassed to admit that I never really understood it. Chances are you do, but just in case, I'm going to break it down. E stands for energy, M stands for mass, and C stands for the speed of light, 186,282 miles per second, or 299,792 kilometers per second. Now square that number, multiply it by itself. That is a really big number. So let's apply this elegant equation to a specific atom, like, uranium. Specifically, the most common isotope, uranium-238. As we learned, atomic mass is determined by the number of neutrons plus the number of protons. For uranium-238, that number is, you guessed it, 238, which is incredibly small, itsy-bitsy, teeny tiny. But when you multiply that by the speed of light squared,
when you change a little bit of mass to energy, it gets multiplied by this humongous c times c squared, which is also just so big that we have no sense of meaning to it. It's just like a big number.
And so, yeah, it's interesting because you can have something that's so small, but when you multiply that number.
Yeah, that number's a lot bigger.
To you or me, just sitting here, the energy released from one single atom doesn't seem like much.
One atom only does give off a lot of energy when it decays, but when we think about like running a light bulb, one atom decaying doesn't give off enough to run a light bulb.
But a chain reaction of fissioning atoms?
It's going to be billions and trillions and large numbers of decaying nuclei, which are going to run a light bulb or a bomb or something.
All that splitting releases incredible amounts of energy, the kind of energy that can power cities or destroy them. This season of Wild Thing is supported solely by First Light Capital Group. Founded by female entrepreneur Alba Toll, First Light Capital Group is an innovative investment firm that strives to generate outstanding financial returns and change how the industry fosters talent and diversity. First Light has a dual-pronged mission. First, it trades public equities, private equities, and debt using its proprietary data-informed investment process. And second, through a separate seed fund, it seeks to cultivate the next generation of female entrepreneurs by providing women-led businesses in the technology and biotechnology sectors with the capital, infrastructure support, and mentorship needed to take their companies to the next level. To learn more about First Light Capital Group, please visit firstlightcapitalgroup.com. Wild Thing fans, I have a serious message for you. If you're not already talking to your kids about aliens, it's probably time to start. Just this year alone, the James Webb Space Telescope found distant planets that might harbor life. Archaeologists claimed to have found mummified aliens, and extraterrestrials even got a shout-out during congressional hearings. No doubt your kids are asking lots of questions, and it could be you're not sure how to answer them. Let me recommend my new book, Is There Anybody Out There?, which arrives on Earth on October 3rd. This middle-grade book, based on Season 2 of Wild Thing, explores the question of whether we're alone in the universe using science, humor, and fun illustrations. And it'll leave everyone better prepared for the possibility of alien life. Help kids learn how to tell the difference between science fact and science fiction. Look for Is There Anybody Out There in all bookstores and online. Or for more information, go to wildthingpodcast.com. It's only recently that we've been able to see atoms, and only with highly specialized microscopes. If you multiplied the size of an atom by 10 million, it would be about the size of a grain of sand. Scale everything else up using that same number, and a housefly is about 44 miles long from end to end. The little old lady who swallows that fly is definitely going to be in trouble. Point being, given the size of atoms, what made scientists realize that there was real energy potential in them?
Really, it goes all the way back to Marie Curie and her first discovery or naming of radioactivity.
Meet Richard Rhodes. If you're going to interview someone about the history of nuclear science, he is your guy. His book, The Making of the Atomic Bomb, won a Pulitzer Prize. The history of the bomb and nuclear energy are thickly intertwined, and neither would have happened without the work of some truly brilliant scientists, including Marie Curie, who discovered the element radium in 1902 and received a Nobel Prize for her work on radioactivity.
So much energy was pouring out of a sample of radium that it glowed in the dark, and it was hot to the touch, although one tried to avoid touching it. But the energy went on and on and on, and there was nothing that was plugged into a wall. So the question really was, what is this and how much of it is there? And the next question, of course, was, is there some way to get it out? And most people didn't think so for a long time.
But that changed with the discovery of the neutron. Scientists knew about protons and electrons. They had instruments that could pick up the positive and negative electrical charges that each gave off. But something just didn't add up. You had these nuclei, supposedly made up entirely of protons, which, by the laws of nature, and thinking back to our magnet example, shouldn't stay together, especially with the heavier elements. That pesky question couldn't be answered until someone figured out that there was something else at play.
There had been a lot of work around basically bombarding atoms with various kinds of radiation, much as one would use a telescope to look at stars. It was a way of exploring them. But normally, the particles that were used to bombard the atoms
To try to break them apart
were positively charged protons, and the nucleus of an atom is also positively charged.
As with the magnets, the positively charged nucleus would repel this proton.
But when the neutron was discovered in 1933, suddenly there was a neutral particle that would be able to pass right through the positive charge in the nucleus and basically just slip into the nucleus with all sorts of extraordinary effects. One of the scientists who was doing the work said the effect was as dramatic as if the moon had struck the Earth.
A true eureka moment that answered a lot of questions and helped scientists figure out how to get the energy out of an atom. As I mentioned before, the process of releasing that energy by splitting an atom is known as fission. And the discovery of this process, in Nazi Germany of all places, took the world by storm.
So that was the beginning of 1939, and there were headlines all over the world. We think of all this as very secret during that period, but it wasn't. It was, in fact, big news. I mean, headlines like Queen Mary ocean liner could cross the Atlantic on one cupful of this material.
A cupful would hold septillions of atoms, which basically sounds like a made-up number. But the point is that it would contain a tremendous amount of energy if you unleashed it.
Anyway, the next piece of discovery was to see if you could get one splitting atom to release more than one neutron. One neutron went in to cause the fission. Could you get more than one out? If so, then you had the possibility of an exponential chain reaction, 1 splitting 2, and 2 splitting 4, and 4 splitting 8, and so on.
And figuring out how to make that chain reaction happen was the next big hurdle. During the 1930s and 1940s, a handful of brilliant physicists around the world had started to puzzle this out. And many people were, in fact, thinking about nuclear energy in terms of its peacetime uses, before they'd even thought about a weapon.
Yeah, because we were not in the war at first. The discovery was just 9 months before the beginning of the Second World War in Europe. So the first focus, really, of the popular press was on the possibility for power. But nobody quite understood it. I mean, there were articles in the popular press about, you'd have a little reactor in your car, you'd have a little reactor in your basement to warm your house, everything that anyone could think of.
The public got all kinds of excited about nuclear power, which we'll get into in the next episode. But it was 2 scientists in particular that turned the hypothetical reactor into reality.
That was the work of Enrico Fermi and Leo Szilard, who was a Hungarian physicist. He and Fermi had the joint patent for the first nuclear reactor.
Fans of Season 2 of Wild Thing might remember Enrico Fermi as the physicist who asked the question, "Where is everybody?" over lunch with his colleagues. They were thinking about extraterrestrial life, and one of the theories that's sometimes given for why we haven't found it is that it already blew itself up with nuclear weapons. Anyway, By 1941, scientists had figured out how to capture atomic energy and immediately recognized its potential, good and bad. On one hand, it could provide a tremendous source of electrical energy. On the other, it could be used as an incredibly powerful and devastating weapon. And as the world plunged headlong into World War II, fears that Germany's fascist government would be the first to develop that nuclear weapon put military needs above all else. The United States entered the war in December of 1941, after the bombing of Pearl Harbor. Less than a year later, Fermi had achieved the first controlled, self-sustaining nuclear reaction. Given the materials he was working with, you'd think they'd have built their reactor out in the boonies, somewhere like Idaho, away from prying eyes and potential casualties. You'd be wrong. He built his test reactor on the campus of the University of Chicago.
It was indeed in the middle of a city, but, Fermi was an extraordinary physicist, and he calculated everything very carefully to make sure.
Enrico Fermi was undoubtedly a genius of the highest order, and probably couldn't get a math problem wrong if he tried. But it still makes me a little nervous to think about building an experimental nuclear reactor under the football field of a big university in the middle of a major metropolitan area. Of course, they had safety mechanisms in place. So while an atomic bomb is an uncontrolled chain reaction, what happens in a nuclear reactor is, at the most basic level, a controlled one. Pete Markowitz again.
So in principle, it's the same as how we create a nuclear bomb, in the sense that we have to have some sort of a chain reaction going on. But there's a difference in that nuclear bombs are much easier because we don't have to control how fast it goes. So if we pick our favorite nuclear power plant, we don't want it to use all the energy at once, because that would be the explosion. Instead, we want it to be in a really controlled, slow fashion, where it's still a chain reaction, but it's barely a chain reaction, so that we could stop it at any time. We don't want it to be an uncontrolled chain reaction that just is growing and growing and growing until it's used all the fuel.
The basic physics of nuclear bombs and nuclear reactors are the same. Scientists are using neutrons to split unstable atoms, which in turn release more neutrons that split more atoms. But with a nuclear reactor, scientists figured out how to slow the chain reaction way down.
So a nuclear power plant is going to have all kinds of devices where you can put something into the reactor core which is going to slow down the rate at which fissions are going to occur.
Rather than 1 splitting into 2, and 2 splitting into 4, and 4 splitting into 8, by adding different types of material into the equation, you can slow that exponential increase.
The way in which we can control it is we have rods which are going to just absorb neutrons, which we can put in or take out.
And rods like these play a key role in what eventually happened at SL1.
So they might be graphite rods. They might be just carbon rods. Boron's good. There's this rare earth. It's called cadmium. It sounds almost like that candy company, right?
Cadbury. I confess to being grossed out by their cream eggs. Anyway, cadmium, boron, graphite. Scientists found that these types of materials absorb loose neutrons easily, which slows things down.
Each fission is going to give off several neutrons, and the reactor operators are going to make sure that, on average, just over 1 of those neutrons is available for the next fission. To keep the reaction rate, the number of fissions which happen every second, you want that to be sort of unchanging. So you're getting out a constant amount of heat energy every second.
Got that? They're trying to ensure a constant rate of fission. 1 atom splits, and only 1 extra neutron goes on to split the next atom. A much slower process.
They would say then that the reactor is in a very stable situation, meaning it's not changing.
And stability is exactly what you want, especially if you're playing with fissioning atoms in the middle of Chicago.
The first nuclear reactor, which Fermi, who loved American slang, called a pile, because it literally was a stack of big graphite bricks with holes drilled into them for slugs of uranium, the graphite serving as the material that would slow down the neutrons. But there was always the possibility that something might go wrong. So he had what he called the suicide squad sitting up on top of this 2-car garage-sized stack of graphite blocks with the buckets of cadmium solution.
Cadmium and graphite would both slow down the chain reaction.
So if everything else failed in the way of controls, they were supposed to, obviously at the sacrifice of their lives, pour buckets of cadmium solution over the pile and quench the reaction.
Fermi didn't think that would be likely, given the scale of the reactor, but he still took precautions.
Fermi knew that his little test reactor, which was called Chicago Pile 1, or CP1, was not going to cause any problem. Its total energy output in the time he ran it one afternoon was about the same as for a flashlight bulb. So there was very low energy production and therefore very little radiation involved.
But despite its size, Fermi's reactor made a huge leap forward for nuclear science.
And that proved that a chain reaction was possible, because this was the first time they had enough critical mass of material assembled to show this experimentally rather than just calculating it.
Now make that chain reaction last for a much larger number of atoms, like, say, a septillion, and you've got the kind of energy that powers a nuclear reactor, or a nuclear bomb. And Fermi's work proved to be critical to the Manhattan Project.
Robert Oppenheimer, the man who would eventually lead the work on building the first atomic bombs at Los Alamos in New Mexico. Within a week of the discovery being published in the British journal Nature, Oppenheimer had a design of an atomic bomb. So as soon as it was clear that you could get a chain reaction, then it was also clear that if you could arrange things right, you ought to be able to make a bomb of truly extraordinary explosive force.
These nuclear weapons and the reactors making fuel for them would be much more powerful than Fermi's small reactor. More power also meant more radiation and more danger. So it made very good sense to move future experiments out of Chicago and into more remote places. Places where, if something went wrong, few people would be exposed, other than, of course, the scientists themselves.
They were aware that radiation could be dangerous, but I would just say during the war, and I heard this from many of these scientists, we knew they said that we didn't have to go fight in the foxholes because we had this particular set of skills. But we were very aware that we had been given that privilege of not being shot at. So we were prepared to take risks.
And many of them hoped they would someday return to developing other uses for nuclear energy, peaceful uses, the kinds that might change America's future for the better.
Nuclear medicine might, cure terrible diseases. Nuclear electricity might make electricity too cheap to meter.
Assuming, of course, we could get past nuclear's darker history.
As the public was being encouraged to start thinking about these beneficial uses of nuclear physics, there was always this cloud kind of hanging over their head that the root of this possible benefit is war and destruction and death. And people had a very hard time separating, what was weaponized and what was scary from what was peaceful and beneficial.
Public perception and plans for a nuclear future. That's coming up on the next episode of Wild Thing. For more on atomic history, I highly recommend reading Richard Rhodes' book, The Making of the Atomic Bomb. And for premium subscribers, we'll also have an extended bonus interview with him later this season. Premium subscribers get each episode early and exclusive access to all bonus episodes, not to mention that warm, fuzzy feeling that comes from supporting the show. For more information, go to wildthingpodcast.com. That's Wild Thing Podcast, all one word. You'll also find out more about this season, including how to get Wild Thing t-shirts and stickers. Links to the website and the shop are also on social media, at Wild Thing Pod on Twitter, Instagram, and Facebook. And please consider leaving us a review wherever you get your podcasts, and definitely tell your friends. All of this really helps get the word out about the show and makes future seasons more likely. This episode was made possible in part with help from the University of Colorado Boulder's Nest Studio for the Arts. And this podcast is a production of Foxtopus Inc., with generous support from First Light Capital. Wild Thing is edited by Alicia Lincoln with sound mixing and music from Louis Weeks. Our executive producer is Scott Carney, and I'm your host and creator, Laura Krantz.